Hi, my name is Veselin Karaganev, and my third-year project is Profiling Guided String Representation Optimizations in TruffleRuby. My project supervisor is Mikhail Luhan. TruffleRuby is a high-performance implementation of the Ruby programming language. It's built on top of the Truffle language implementation framework. It's written in Java, and it's an alternative to the widely used reference Ruby implementation called MRI. TruffleRuby itself is a self-modifying interpreter and uses a graph-based intermediate representation. Self-modifying means that the graph of nodes can be changed at runtime, and new machine code can be emitted from it via just-in-time compilation. This can be done to avoid paying the cost of expensive runtime checks by omitting them from the code after profiling, or to replace one implementation of a method with another more appropriate one. User reports on the TruffleRuby issue tracker point to some performance issues in the implementation of the string data type. One particular report identified a benchmark which ran much slower than expected. After profiling the code, it was clear that the majority of the processor time was being spent in the string assignment operation. The benchmark in question used an external image processing library which stored the pixel data from images in strings. Modification of the pixel data was done by modifying the string itself. The Ruby language does have mutable strings, and this means that users of the language will often assume that these operations are fast and inexpensive. What's more, the reference implementation of Ruby MRI uses array-based string implementation, which has these properties. TruffleRuby, however, uses a more sophisticated tree-based data structure called a rope to implement strings in Ruby. Strings are a core data type available in most programming languages and are widely used in a variety of important use cases. The main objective of this project is to fix the performance issues mentioned without negatively affecting these other use cases. Ropes are an immutable tree data structure in which character arrays represent the leaves of trees, and the operations between them, like concatenation, repetition, or slicing, comprise the internal nodes of the tree. By traversing the tree and applying the appropriate transformation, all characters of the rope can be enumerated. Ropes can be beneficial in a lot of situations because they exhibit laziness. Enumeration of the tree does not need to happen after every operation. Because they are immutable, however, mutation operations such as changing a single character in a string are represented by constructing another tree representing the merger of the left and right partition of the former rope, adjoined by a new character. This is done even in the case shown in the diagram, where the target rope is comprised of a single leaf rope with a backing character array. Structural sharing is the reason why the backing array of leaf ropes cannot be safely mutated. In the following code snippet, we see 4 string values being assigned to variables. The values of B, C, and D are all derived from the value of A, and because ropes exhibit structural sharing, the leaf rope representing A will be referenced from the 3 other ropes. If we were to simply modify the array of the leaf rope A, that would also change the values of B, C, and D, which is not what a Ruby developer would expect. By tracking whether the leaf rope has been referenced by other ropes, we can tell when it's safe to change the backing array of that node, knowing that it would not lead to unpredictable changes in other values. Here is how this works. String A is represented by a leaf rope which is mutable as indicated on the slide. While the flag is set, we know that the node is not referenced by other nodes. When a substring of that string is created on line 2, the leaf rope node becomes referenced by the substring rope node, and the flag is changed to indicate that the leaf rope of A is now read-only and not safe for mutation. This node will remain read-only for the remainder of the program. The presented implementation can convert read-only ropes to mutable ropes when needed by copying the underlying array and creating a new leaf rope with the mutable flag set. This works well in the majority of cases, but as shown in the example on the slide, it can also lead to slow code that allocates a lot of extra objects. This is because if the string on line 2 is not a mutable leaf rope, the tree needs to be flattened and a new mutable leaf rope needs to be allocated. When the concatenation on line 3 is executed, the newly allocated mutable leaf rope is made read-only by changing the flag, and then the cycle repeats. A new profiling technique was developed to detect these situations. By remembering the last result of the mutation operation on line 2 and comparing it with the new target value when line 2 is executed again, we can deduce whether the rope that was allocated was reused in the next iteration of the loop. This is referred to as rope reuse in the paper. Low rope reuse indicates that the rope is likely not a good candidate for the mutable rope optimization, and in that case the existing concatenation-based implementation is enabled by rewriting the DAG. Several other optimization techniques were explored. The dynamic array optimization allows the buffer and mutable ropes to be over-allocated so that the consecutive string append operation can be performed in place. The small string optimization eagerly evaluates small ropes with the intention of avoiding large tree structures. With the mutable rope implementation enabled, the execution time of the ray tracer benchmark mentioned in the user report was improved by more than 800 times over the baseline TruffleRuby implementation. Other string-intensive benchmarks were used to control for and detect performance degradation in other parts of the implementation. The dynamic array implementation had mixed results and resulted in increased performance in some benchmarks and lower performance in others. Finally, the small string optimization did not result in any performance improvement when used standalone. In summary, the project achieved the objectives that were set. Improved data structure design and the new profiling technique were implemented. The performance of the described use cases was improved by close to 3 orders of magnitude. There was no performance degradation observed. The mutable rope implementation will be made publicly available and will be suggested for inclusion in the upstream TruffleRuby. More work needs to be done on the dynamic arrays for mutable ropes implementation to close the discovered performance gaps.